Hey, welcome back everyone to another Toolbox Tech Talk.
Every word that comes out is a lie. Make it look like it's so ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable.
Yeah, it's that time again. Sunday, 1 o'clock here. Still the last dregs of daylight saving in Victoria. Yeah, so thanks for those who sent in some questions. Good to have some feedback from you over the week, and also just in the last few minutes, a few emails that come flying in. It helps if I get them a little bit earlier than the last few minutes, especially when they're long and technical. But actually, shout out to Yariv. He gave me a great one on lightning protection. So I think that's going to be a whole topic for another Toolbox Tech Talk. Will be lightning protection systems and 5033. In fact, 5033 has a really good section on lightning protection written by one of the global authorities, he's done a fantastic job. So we might dive into that. G'day, Lotha from Thailand. Wow, yes, my first viewer that I know of who's from Thailand. Great to have you on board. And yes, Yariv, yes, you're here too. So Yariv, in case you missed it, I'm going to devote a whole session to lightning protection. And Martin, hi. Yes, it's Eid Mubarak at the moment. So, yep. Good on that. All right. So, yeah, today is kind of like just a mixed bag, really. I don't have a big topic. It's answering a mismatch of your questions. But before we dive into that, the usual thing, I just wanted to let you know about the Smart Energy Expo one more time. I will be there. So, if you really want to say hi and catch up with me, that would be great. You can just come and join me at the Smart Energy Expo in Sydney. So there it is there. It's in the 9th and 10th of April. I'll be dressed somewhat similarly to you see me every Sunday with my gold chain on. It's funny, it's become my signature chain. People just know me by it. So, even though it's a bit of a silly joke, it makes me stand out in the crowd. So there you go. So look for the gold glint, and don't be mistaken, there's a couple of other people who wear gold chains that I awarded. So I mentioned them last week. Yeah, so Thomas and Dave, they're awardees of the illustrious gold chain. So, yeah, that's the Smart Energy Expo. And, so let's go back to me. So what we're looking at today is a bunch of questions, things like how to calculate the voltage and current, the maximums that are required for battery systems under 5139. Where do the labels go? Do you have to stick them on the inverter? Where can you put a battery in a building that contains habitable rooms? Just a bit of clarification on that one, because there's been a few confusions. And also from Stephen Zelm from South Australia, who's asking about RCD protection on vinyl subcircuits for alternative supplies. We're going to cover that. How to test for earth fault. So I did a whole series or session last week on earth fault and the requirements for earth fault detection, but also I didn't cover how do you measure an earth fault and find one. And lastly, in terms of the pre-questions, and just a reminder, please feel free to throw some into the chat if you've got some that you want me to answer live. The last pre-question I got was about PV arrays and orientation, and I've got some fun stuff to tell you about on PV array orientation. It's not as simple as it used to be. So there you go. That's the rough program for today. So let's start with, where are we? Toolbox Tech Talk slides. There we go. Okay, so for those who are new to the channel, by the way, I do, this is a live session, but it is watchable at any time afterwards. You can just go into my my channel on YouTube, Smart Energy Labs, and it'll be there, so no problem. So first one is on battery labelling. Now, this has become a bit of a sort of a niggle for me, is the way labelling is done. So it's not complete, it's excessively over-complete. I'll explain what that means. And it's often done in a very ugly way all across the front of your beautiful battery BESS system. Oh, g'day, Ian from Weenie Creek. G'day, Ian. Good to have you on board. And Scott from Geraldton. Wow, we've got a bunch of people from all over the world now. That's great. So, yeah, it's one of my pet hates. So, battery labelling. In the standard 5139, it says where a battery system has individual cells or modules or are able to be accessed or serviced, each individual cell or module is required to have a unique identifier, including the use of consistent terminology. So battery 1, battery 2, battery 3, or module 1, module 2, module 3, if you've got a rack of them. The label shall be placed on each cell or module. Now, unlikely to be cell level, because that would be a very granular kind of DIY system, but these days generally cells are packaged into modules, something useful like a 48-volt module or similar, and those are either rack-mounted, stackable, or ground-mounted. And on each cell or module such that it can be read without moving the cell or module. So, yeah, labelling that's not visible without disassembly is not appropriate. Where there is a battery management system, a BMS, for the cells or modules, the labelling shall be consistent with the identification from the BMS. So this really relates to things like shutdown procedures. Now, I did cover in a previous Toolbox Tech Talk that you don't actually need a one master e-stop for a whole BESS or battery system. You might have, as I have in one of my systems here, we've got 40 battery modules all in parallel. We don't need one big isolator for the whole 40 systems because it would be several thousand amps of switching. You can use individual switching on each battery module as long as it breaks both conductors, a positive and negative, and it's labelled. So, and the shutdown procedure should reference those labels. So, for instance, in my case, it will be saying to shut down the battery system, switch off battery modules 1 through to 40 to isolate this system or this battery system. So, yeah, you don't actually have to have one big master switch. In terms of other equipment, things like meters, shunts and alarms shall be labelled. For instance, if you've got an energy meter and a switchboard, it should be some indication what that metering is for. And it's really important that labels match all the documentation. So if you're using words like DC isolator and DC switch interoperably, they're not. This system is going to be often operated by someone who's not trained in electrical language, and they want to just be able to look for something that's called a DC isolator, and the label should say that. Equally, if your shutdown procedure lists shutdown inverter by turning off main switch inverter, make sure that that's what the label is on the main switch, not something different. In fact, I've done a session on main switch labels in a previous Toolbox Tech Talk. If I'm smart enough to remember, I might be able to link it up here. It always takes me a while to remember to go and put those links in after the recording. But things like what we used to think of as a main switch for backup systems has now got different names. It's known as an alternative supply. And where you've got a system such as an inverter that can be fed from the grid but doesn't export and can be providing a independent supply to an installation that's now called independent supply, funnily enough. Yep. But yeah, so go and check out, if I remember, to put the link in here. You can't see me pointing, I just realised I'm pointing up there. But that'll be for the post-recording edit. There we go. So that's one thing about battery labels. The other question, which is kind of related to labels too, is what do you put on the voltage and current label? There's a requirement to have the maximum battery voltage and short circuit current. Now, I think we kind of did a poor job in writing the standard for this clause because it's sort of written as if every system has accessible battery terminals that you therefore need to know what the fault current at those terminals can be. But for a fully integrated system like a BESS, say, if you're using, for brand names, something like a Tesla Powerwall or a SIG Energy Cygen Store or a SoFar Solar all-in-one, there is no accessible battery terminals. They're all sort of interlocked within the system, so there's only an AC output and PV array inputs. So in a way, this clause is a little bit difficult to comply with. So let me take the example of, since I know it quite well, the SIG Energy Cygen Store. The battery modules internally are made up of a bunch of prismatic lithium ferrophosphate cells with a nominal voltage of per battery pack of about 32 volts. But nowhere can you access that 32 volts because it's internally within the battery module connects to a DC-DC converter, and the DC-DC converter steps up the voltage based on what the PCE requires. So if you've got a single phase PCE, it'll be up around the 400, 500 volt mark. If you've got a three-phase PCE, it could be 700, 800 volt mark. So the PCE actually determines the voltage of the output. But once again, the output is internal. I mean, it's not accessible. It's not like you, when you're working on the system, you're exposed to those potential hazards. So I think really it comes down to manufacturer's statement. So if the manufacturer provides you with, particularly when it comes to a fully integrated system, a fault current and a maximum DC voltage of the battery system, that's what you'll be putting on there. Please note on that second highlighted clause, for systems over 60 volts DC, that's above DVCA, you require the hazardous DC voltage sign as well. So that's just to indicate there's a higher risk. And where there are multiple battery systems or BESSes installed, the following apply. Only one sign is required if all the systems are in the same room. Now, you've got to often try and think about the intent of a standard here, certainly when it's not very prescriptive. This is first responder information. They'll do with it what they were trained to do. So if it says something, that they've been made aware that they shouldn't spray water on it because it's potentially a dangerous conductive voltage, they will respond to that. The current shall be the maximum short circuit current calculated for any of the BESS, and where each BESS has a multiple battery system connected in parallel, the calculated current shall be the sum of the battery system short circuit current of each of the paralleled systems. So in my case, with 40 battery modules in parallel, I've got to sum the fault currents of all 40 of them to get the maximum prospective fault current. And so I approached the manufacturer to find that out. When this standard was first published, by the way, there was a lot of confusion because a lot of manufacturers just assumed that if there was internal overcurrent protection on a battery system, like a circuit breaker or a fuse, that would be the short circuit fault current, but it's not. A short circuit fault current is the peak before the tripping occurs, because that's a point where an arc can be struck, even though it'll be extinguished as soon as the trip occurs. And in the case of, say, LG Chem's Resu 10, the Resu 10 units, 10 kilowatt hour units, which are nominally a 56 volt nickel metal hydride, NMC, nickel manganese cobalt battery. The breaker is 160 amps, but the fault current, according to the manufacturer, is 2,250 amps. So yeah, it's way more than just the overcurrent protection device itself. Okay, I'm just checking for questions in here. And g'day, Adoro from Mexico. Hey, wow. That's my first person from Mexico. And Manoj, nice to have you. And he's asking for my email address. So I'm happy to share my email address in the chat because you can send me suggestions and questions for future Toolbox Tech Talks. Martin says, are systems installed prior to 5139 required to add this labelling? We've never been retrospective with any of our Australian New Zealand standards. The only time something kind of retrospective applies if you modify the power, voltage or current of a system, you need to bring it up to current standards. So no, Martin, you don't have to go back and relabel all those old systems. Just beware, if you do change anything, it may be, unless it's a like-for-like swap, a requirement to meet the new standards. Now, Martin's actually in New Zealand, and in New Zealand 5139 or ASNZS 5139 being a joint standard published in 2019 is yet to be referenced to New Zealand electricity regs. Now, I say this an awful lot, but there's always a few new Kiwis joining my live streams, and so it's not required under inspection at the moment, but it is provided as best practice advice. And WorkSafe New Zealand said to me in an email that even though it can't be enforced, it can be used in a court of law. Okay, take that for what you will. I've hearing good news from the Minister for Energy, the new Minister for Energy in New Zealand, Mr. Watt. What a great name for a Minister for Energy, Mr. Watt. That's highly likely that New Zealand will get an update to New Zealand electricity regs probably mid-year. Now, we've been holding our breath for so long we've turned blue, but let's just wait and see before we celebrate that one. It will be very good for Kiwis to have current safety standards available. Now, where are we up to? Back onto my slides here. Okay, now a little bit of an explainer here. And maybe a little bit of a mea culpa too. So a few people in a previous Toolbox Tech Talk, I think back on the 2nd of March, I think Alan pointed it out to me. I didn't make it very clear when I said you can't install a battery system under a roof that contains habitable rooms. I did actually say, as part of that statement, if it's a Section 6 battery. Okay, so I better explain what these sections respond to or relate to. So 5139 really is kind of addressing 3 different types of energy storage systems. What we call Section 4 is for a pre-assembled integrated BESS. That means the inverter or the PCE, to be more technical, and the battery system are one product. They can actually be separate, not physically within the same enclosure, but there must be no on-site manufacture of parts. And additionally, they need to meet what's called the best practice guide. The best practice guide is really a cobbled together document to provide a quasi-product standard for energy storage devices. And it is currently going through a committee review. Now, it's not an Australian standard or a New Zealand standard. It's actually just an industry document, but it's referenced in 5139. So Section 4 would be things like this, a Sage and Store system, or a Tesla Powerwall, or a Sofar Solar all-in-one, or an Alpha ESS all-in-one. They all meet that requirement of being pre-assembled battery storage systems. The Section 5 is where those are separate components. The battery system is a pre-assembled battery system. In this case, I'm showing a BYD HVM, I think it's an HVM, and a separate PCE, in this case the Fronius Gen 24. They're a very popular combination. I've got exactly that here at the lab. Looks like they even colour coordinated them. So where Section 5 really only applies to the battery system because you are now installing DC cables, so cables between the pre-assembled battery system and the PCE, and therefore you've got to consider overcurrent protection, mechanical protection, isolation, quite a few extra things with the Section 5. But both Sections 4 and 5 are kind of put into a category where we're fairly confident in the product's reliability and safety, or I should say safety. But Section 6, now I'm not casting nasturtiums, as Kath and Kim would say, for those who don't know Australian comedy history, who don't cast assertions, sorry. I'm not saying that Victron is a bad product or that the King battery is a bad product, but it's got nothing to do, with the PCE. Section 6 is only about the battery. And in this case, this battery, even though it's a lithium-ion battery, isn't listed as a pre-assembled battery system compliant with the best practice guide. It might have a bunch of IEC certificates, but unless it's, in the case of Australia, it's fairly easy to find out. The Clean Energy Council manage the approved product listing, and that means that they have confirmed that the product is appropriate for sections 4 or 5. And if it's not in 4 or 5, it won't be on their list. Section 6 is deemed to be of kind of somewhat unknown. Now, there's a bit of rankle about this Section 6 because some of the safest technologies end up in Section 6. Things like redox flow batteries, nickel chloride batteries, batteries that have no explosive gases or thermal runaway potential, but they don't have a product standard. And so when 5139 was written, we couldn't refer to a product standard for those chemistries and therefore put them into a safe category. So Section 6 is kind of the catch-all for everything else. Unfortunately, some of the safest and some of the questionables all end up in Section 6. Now, the reason I'm going to so much trouble to tell you about this is because it relates to the next slide, which is restricted locations. Now, restricted locations in Sections 4 and 5, if you look at the clause number at the top there, 4.222 and 5.222 are identical. So your pre-assembled BESS, 4.222, and your pre-assembled battery system, 5.222, have exactly the same restricted locations. But when you get to Section 6, there's one additional point in that list, and it says a restricted location is under floors of habitable rooms. So, for instance, in a garage with a bedroom above, Section 6 battery can't be installed. No matter how much you want to put a fire barrier around it and, make a highly protected environment, it still doesn't cut the mustard. So Section 6 basically says you can't put it under the floors of habitable rooms. And habitable rooms are defined in New Zealand, in the building code, in Australia, the National Construction Code. But, it's the fairly obvious ones: bedrooms, lounge, kitchen, study, places where people spend extended periods of time. And non-habitable rooms are things like garages, utility rooms, laundries, walk-in wardrobes. I know that's a funny one. You can't put a battery in a bedroom, but you can put it in the walk-in wardrobe. But there's still some requirements about clearances from a doorway, 600 mils. So it's got to be a big enough walk-in wardrobe you can get the battery away from the door. But there you go. But Section 6, not under the floors of habitable rooms. But there's a sort of related clause. I think I've got my slides in the right order here. Yes, here it is. So for Section 6 batteries, we're focusing here on arc faults as well. And with arc fault analysis, we calculate the prospective incident energy from a arc from the battery system. And as you can see at the very top there, it says for battery systems installed within residential or domestic electrical installations, the arc flash value shall be less than 40 cal per square centimetre. Now, I've done a previous Toolbox Tech Talk on this, and way, if I can remember to link it up here afterwards, I'll try. Otherwise, you've got to just trawl through my previous ones. That's going to be hard work. And a 40 cal per square centimetre is incredibly high arc flash level. You're talking a full space suit, basically, one of those shiny suits, ear protection, hard hat. You basically look like you're going to walk into a furnace. So anything over 40 cal, not going to be in a residence installation. But where the battery system has an arc flash value greater than 4 cal, the battery system shall be installed in a dedicated battery room or enclosure not attached to the building containing habitable rooms. So you really want to get below 4 cal, and you need to meet the requirements of fire hazard level 1. Which is another topic, which I've probably also covered in the previous Toolbox Tech Talk. If the battery system is installed externally and not connected to the building, you can actually go up to arc flash energy levels of up to 8 cal per square centimetre. Now, I have produced, maybe I can just dig it out right now rather than tell you stuff that you have to go and look for. I have produced a spreadsheet calculator for this purpose, and I'm just looking for it now. Where are we? And it'll be under some of my software, ArcFlash. Here we go. Okay, so it's a spreadsheet. I'll have to work out a way to share this. I'll probably put a link in the description after this is published, so you can download it. But it's just a really simple spreadsheet with calculations. And if I bring it up here, here we go. So it's probably a little bit small, but what you need to do is plug in some values. Now, let's take a lead acid battery system, just for contrast, because we're talking about lithium an awful lot. And so I'm going to zoom in a little bit here. Okay, so we're going to do a lead acid battery system. So its nominal system voltage is 48 volts. Now you'll notice that the I arc, which is the arcing current, you can't click on it. We're going to skip over that because what you put in is the bolted fault current, and that will calculate the I arc automatically. That's what the spreadsheet does for you. So the bolted fault current is the peak current when no overcurrent protection is you're circumventing any overcurrent protection on the output of the battery system. So in the case of a lead acid battery, the most positive and negative terminals, you put a nice big copper bar across there, and what is the fault current? Now, I don't do that. Please do not do that. What you do is you go to the manufacturer and ask them what is their maximum fault current. It can be expressed in milliamps per cell, and you can just divide the cell voltage by the milliamps per cell to calculate the current. But let's say this is a 1000 amp hour lead acid battery, pretty popular for once upon a time for off-grid, and it'll have a bolted fault current of about 11,000 amps. Now that sounds ridiculously high, but that's one of the amazing things about lead acid batteries is they're extremely high prospective fault current. The arcing time is half that. So IARC, is half that. Now the arcing time, it says if there is no string overcurrent protection within the string of cells, or in the case of lead acid battery, the actual battery cells, then you use 2 seconds of arcing time. And 2 seconds of arcing time, and then you need to put in what the working distance is. Now, working distance is deemed to be arm's length, 45 centimetres. Unless you're using a robot or something. The multiplying factor is to do with whether it's installed in the open, in a building, or in an enclosure. So I'm going to put it in an enclosure, which gives the highest multiplying factor, 3. So I've got a battery box, and it focuses that arc flash incident energy. And you'll see that we got up to 7.8 cal. Whoa. So that means it can't go, this lead acid battery, because it's section 6 and the arc level is above 4 cal per square centimetre, it can't go in a building under the roof that contains habitable rooms. So it can't go in an attached garage, for instance. It can go in an external building because it's under 8 cal, but only just. So it can go in an external building. Now, the second part to this calculation is the incident energy boundary. So the arc flash incident boundary is the zone to which PPE is required. So let's fill this one out, 48 volts. Arcing time is 2 seconds. Bolted fault current is 11,000 amps. And we've got 1.15 metres. So for those who are imperial, it's probably about 4 and a bit feet, I'd say. So within that sort of zone, you need to have PPE, and the PPE requirements are listed below. So if we go down here, this is a 7.8 cal fault current. So we're basically looking at category 2. So up to 8 cal, between 4 and 8 cal, we're category 2. So that's quite a lot of kit on. Arc-rated long-sleeve shirt, arc-rated pants, overalls, arc-rated shield, balaclava, hard hat, safety glasses, hearing protection, leather and voltage-rated gloves, leather work shoes, wool, just to top up the water in your lead acid battery. You try and explain that to a customer. But I do have good news for you. The good news is it's very easy to massively reduce using exactly the same battery, the arc flash instant energy and boundary with a $20 product. It's called a fuse. So if you put a fuse within the string, so let's say you've got a 48 volt battery system, it's lead acid, it's made of 22 volt cells. Sorry, not 20, what am I saying? 24 2-volt cells. It's been so long since I've done a lead acid battery, I've forgotten that. So in the midpoint, around between the 12th and 13th cell, we put a inline fuse. And that fuse means that the arcing time can be considered to be 0.1 of a second or less if you've got the time current series for that fuse. And look what's happened. Suddenly we've gone from 7.8 cal to 0.4 cal, green light. Green means insignificant. So it's gone from wearing a lot of PPE to insignificant. And so the boundary, well, if it's insignificant, we probably just need a pair of safety glasses. There you go. That would be kind of, I know it says no protection, but then they've got someone with safety glasses on, maybe because that's always a good thing to have when there's stuff that can go bang. So there you go. That's a little aside on arc flash protection. So, gee, I got a big sidetrack there, and I see there's been some questions come in already. Adam, g'day Adam. Can I plug a generator into a SIG Energy gateway if I get a blackout? Apparently 3000 standard requires that the generator is hardwired and my ad hoc use would not be allowed. That's correct, Adam. So this is not new. It's got nothing to do with SIG Energy at all. It's been a requirement since the early days of AS/NZS 4509 Part 1. It's reiterated in 4777 Part 1, is that where you have a interactive inverter, one that can parallel with another source, like a generator, the generator needs to be connected by fixed wiring. It can't be a plug-in. Now, this is extremely poorly complied with in the off-grid world. So, just because people can do it doesn't mean it's allowed or it's right. Now, there's a logic to this, and I've even tested this and found the safety issue. It is that when you unplug a generator, which will be supplying a male pin socket inlet to your inverter. So your inverter's got a male pin socket inlet, and you're connecting the end of an extension cord, which is a female plug. The moment you unplug that, you would think that those pins are no longer live, but there's no test for that. In 4777 Part 2, there's no test for that, and I have personally come across some which are live for a few seconds afterwards, and I've even found some which were live the whole time, and I suspect that was a product firmware failure or something had gone wrong with the system, but those pins were just sitting there waiting for you to touch and potentially have a fatal shock. So that's the real reason behind it being fixed wiring. I'll hear people say, but how come in Europe, countries like Germany and Netherlands, etc., you can have a balcony power system that you plug in? Well, in those countries, the VDE, which is their standard for inverters, actually has a test for pluggable devices. And so if the device complies with the pluggable requirements of that VDE, I can't remember the number off the top of my head, then it's deemed to be safe. So I've got here in the lab an Anker Solex system I've been testing and using the oscilloscope and capturing the disconnection point in real time. It's something in the realms of less than 200 milliseconds. In fact, it's more like a fraction of a millisecond is the disconnection of that live pins. So they meet the VDE standard. But we don't have that in our standard in Australia. Personally, I'm in favour of it. If we did have a test standard, I think it's a very useful thing to be able to have a portable generator that you can plug in. But there is one more reason why it's not a good idea. Now, when you program an inverter for an energy source, you need to know what the capacity is of that energy source. Now, let's say it's a 12 kVA genset. So you decide to draw around about 75% of that. So let's say around about 9 kilowatts of power off your 12 kVA generator to charge your battery system. That all works fine. But if it was a plug-in generator, it doesn't actually always be the same generator. So that generator goes away or it dies. times are tough, cost of living crisis. So you just go and buy yourself a little Honda 2 kilowatt unit and you plug that in, and the inverter then tries to draw 11 kilowatts out of your little Honda 2 kilowatt unit, and it just stalls or worse. So that's a kind of practical reason for it as opposed to a safety reason. So another question here from the PN Solar. Hi Glenn, earlier this week there were some questions raised around 4777 part 1 5.3.1 and the last sentence, a single phase alternative supply shall not be connected to any phase of a multi-phase system, final sub-circuit or sub-main. Can you explain the intent behind this, says Jim. Jim, I'm aware of this clause. I might take that question on notice so I can do a little bit more background on it, because I assume it's to do with phase balance, but I can't be sure. So let me take that one away, Jim, and I'll add it to my next intro questions on the next Toolbox Tech Talk. But really appreciate you asking the question. So where are we? I'm going back to my slides now. Okay, so we've covered arc flash and why you can't put a Section 6 battery with a high arc flash in a building containing habitable rooms. Okay, now one, I think this probably relates to Stephen. So Stephen sent a question in on this one, alternative supply. Now, just to define my terms, so we used to talk about hybrid inverters having a grid supply and a backup supply, and they're often labelled such. Oh, you can't see the slide. Whoops, sorry. There we go. So a alternative supply is the new supply naming used. Well, it's not that new to 3000, but it's new to 4777 part 1 for a backup circuit. So if you have a hybrid inverter that has a backup, it's now known as an alternative supply. It's an alternative to the normal supply, which is the grid. Okay, so it's kind of logic. And we decided that as much as possible, we'll align with 3000 for any of our supply names. So final subcircuits supplied by alternative supply from an IES. IES, don't we love our TLAs, our three-letter acronyms? Inverter Energy System or systems is another way of referring to an inverter. It's a little bit more sort of generic. So final sub-circuit supplied by an alternative supply from an IES shall be located in a dedicated alternative supply switchboard. So take a deep breath. Oh my gosh, I've got to put in a new switchboard every time I have a backup circuit. But there's an exception. We love our exceptions. We're not reasonably practicable, and you can argue that one. The alternative supply final sub-circuit shall be located in a switchboard with other circuits not supplied by the alternative supply. The alternative supply final sub-circuits shall be grouped. So effectively, if you've got let's say you've got a two-way board, you might have all your grid circuits on the top and your alternative supply on the bottom rail, or you may use space between them, so actually have a segregation and label to indicate which live when the grid's not available. So there you go. So that's the alternative supply switchboard arrangements. And then it goes on to say protection requirements for those final sub-circuits. All circuits supplied by the alternative supply shall conform with ASN ZS 3000 requirements for protection and RCDs. So maybe, Stephen, to answer your question, it's not actually mandating RCDs, it just needs to meet the requirements of 3000. So if 3000 says you need an RCD on a stove, then you need an RCD. If it says you don't need an RCD for a particular application, then you don't. So it's really just falls back onto 3000. I hope that clarifies your question, Stephen. I'm looking down here, no more new questions come in. Now, I had a question from Alan, which was, you talked about earth fault detection last week, but what about trying to find an earth fault? Now, this can be a bit of a nightmare for a couple of reasons. One of them is that earth faults are not always constant. So you may well have a system shutting down often in the morning when it's a bit dewy or it's been raining, and then the system starts working later in the day. So what you've got is a bit of moisture ingress somewhere into the system that's creating a low resistance path to earth, and therefore the inverter is detecting that leakage and shutting down. So first problem is actually to replicate the fault. I've heard of stories where people get a hose and hose the panels and try and get everything as wet as possible to replicate the fault. But that's challenge number one. Of course, the steps here always start with safety first. So make sure you isolate the array from the inverter, use the appropriate PPE, because you may be touching something that has got an earth fault on it. So there may be some live DC. Follow all of your electrical codes and manufacturer's guidelines, of course. The equipment, typically something people refer to as a Mega, which is a brand name, of course, but an insulation resistance tester. Now, people sometimes say, 500 volts I should use because, panels, can they take 1,000 volts? Yes, any panel tested to the latest IEC 61730 is actually tested to 2,500 volts, but then it's rated to either typically 1,500 volts or 1,000 volt on the manufacturer's label. So they can happily take 1,000 volts without causing any harm to the panel. You're going to need a multimeter as well for some basic continuity checks between conductive parts like the frame and the positive and negative output of the array. So the step would be isolate the array, turn off the PV systems isolator and DC disconnection devices. Ensure all inverter connections are isolated and open circuited from the PV array. A visual inspection, that's often a good place to start. Is there anything being damaged? Have we had a hailstorm and there's broken panels? Is there signs of internal failure within the module? So a module might have signs of burning or brown spots. And look at the plug and sockets. Now, last week we covered a case study on a system that the plug and sockets had failed and there were burning holes in the roof from arcing. So then go and measure the resistance. So test each string. So you're going to test between positive and earth and negative and earth, presuming it's a floating array. Now, it is possible to have a non-floating array. That means that one positive or negative is directly connected to earth, but not if it's connected to a transformerless inverter connected to the grid, because you'd be basically shorting it out to the grid. So the only time that you'd ever have positive or negative connected directly to earth would be in an off-grid system where you've got a functionally earthed battery and you could therefore functionally earth your PV. It's almost never done anymore. It just saves you one fuse and raises a whole lot of extra problems. So floating arrays are the norm. Set the insulation tester, to your 5 or 100 or 1,000 volt range and check what the impedance is. So resistance, because it is DC. The resistance should be greater than the mega ohm, ideally 20 mega ohms. So there is actually some guidance in 5033, depending on the size of the array, the number of kilowatts, what that value should be. So check that. So there you go. That's step one, or step three, I should say. What about the results? So yeah, you can see the potential for failure if you get a relatively low reading, particularly if it changes when you spray water onto the system. Also do continuity checks between earth and the DC conductors, and make sure that all your module frame rails are properly grounded, properly earthed to less than 0.5 of an ohm, which is the requirement in 3000 for protective earthing. It's also the requirement for equal potential bonding in 5033. And there you go. So rectify the faults, tighten all loose connections. If you wonder where this list came from, it's from my favourite assistant, Mr. ChatGPT. It's the secret weapon for getting stuff done quick. So there you go. But of course, it does actually give you references now in ChatGPT where the sources are, so I can check that the sources are good. So there you go. Okay. I think we're at the end of my pre-prepared question and answer. So, g'day, Anna Themba. Good to have you on board. And so now's your chance to throw some questions at me. We've only got a few minutes left before I was going to wind up. But what else can I tell you? Oh, yes, hang on. I forgot. Oh, no. Got more questions in my list. Sorry, that was just my slides. So what are we up to? PV array orientation. Yeah. So this question came in today, actually, just in time for me to draw a little drawing. What is the best PV array orientation? Where should you point your panels? So this is kind of an interesting question with over time how things have changed. So let me bring up my little famous drawing pad here, piece of paper and a pen. So what I've drawn here is a load curve for a residential system, and I describe this as a household. There's no one at home during the day. So we've got a spike of power in the morning for morning cooking, maybe some dishwashing, and then this little stepped line here is the fridge turning on and off, some cycled loads, and then coming home in the evening and some cooking and air conditioning, etc., and the loads go up, and then a bit of watching Netflix and chill, and then go to bed. There you go. So there's your load profile. Now, if you're looking for the maximum production of a PV array, in most circumstances, the optimum is to face the panels towards the equator. So in the southern hemisphere, that would be face the north, and the opposite in the northern hemisphere. So if you face panels north, you'll get a very distinct bell curve on a sunny day that looks something like this. So this is our solar production. And it will peak at solar noon, not necessarily clock noon, by the way, at solar noon. That's when the sun is perpendicular to the panels, if the panels are facing true north. Now, if you think about this, the self-use in this system is the area under the loads. So the solar is covering all of those loads. And what's going to happen to all of this above the load level? Well, it depends on your connection agreement, or if you're on-grid or off-grid, if you have a battery system. If you have no battery, it's either going to be curtailed because you're export limited, could be as bad as zero export, so that curve might actually never happen. It might just bump along following that load line, or you export all that at, these days, certainly in Australia, the export rates are very poor. The default rate, I think, for Victoria now is 0.02 of a cent per kilowatt hour. I call that zero without saying zero. So, yes, there's a missed opportunity unless you can use it. But of course, if you have a battery system and it is sized sufficiently to capture all of that surplus above the line, then that's a good story, because that can then fill in the gaps in the evening when the sun's gone down. But for a solar-only system, there's another approach, which is try to match the orientation of the array to the loads. Now, this might seem kind of counterintuitive, like we're not going to face it to get the most notional production, but we're going to get the most self-use. So we might have a somewhat lower east-facing. So this is our east-facing solar, and we'll have a west-facing solar. Of course, it'll vary with season as well. So now you've got a lot more coverage at the beginning of the day with the east-facing array, and at the ends of the day with the west-facing array. And in summertime, depending on your latitude, it's quite significant how much stretch you'll get. So the further you're away from the equator, the further you towards the poles, the greater that variation in summer to winter. So here in Melbourne, in Victoria, we'll be getting the sun setting rising in the southeast in the morning and setting in the southwest in the afternoon. So we're picking up those ends of the day, which is, particularly in the afternoon, it's like air conditioning loads in summertime are being covered very nicely. So it's not all about notional maximum theoretical production. It's in the case of a solar-only system without batteries, it's really about the maximum self-use of your energy. Now, there is some other tricks you can do. If you don't have a roof that's suitable for having an east-west array or something a bit close to that, maybe a north and a west or a north and an east, you could try and move more of these spiky loads into the middle of the day. Now, it doesn't mean you have to stay at home. There's a lot of appliances that can be scheduled. So scheduling things like dishwashers, clothes dryers, swimming pool pumps, EV charging, all of these things often can be scheduled to happen when the sun's shining. So, yeah, it's not as simple as that. But further to this question, someone said to me, what about, they happened to notice on a visit to my lab that I had panels facing south on one of the houses. Now, I wanted to kind of address this one. And I often say south is the new north. Why do I say that stupid thing in the southern hemisphere? But it's because the north is often full. You've already put solar up there. You might even have solar hot water. There's no more room on the north, but the south side of the roof is empty. Now, is it worth putting panels on the south side of a roof? Well, let me use data as opposed to my vibe. So let's bring up my... Here we go, a little spreadsheet. So what you're looking at here is for Wanaka, New Zealand. So somewhere pretty south. Wanaka's around about 45 degrees south, nearly halfway to the South Pole. And what I've got here is the amount of peak sun hours falling on a roof for different tilt angles. North would be flat, 10 degrees from horizontal, 20 degrees from horizontal, 30 degrees from horizontal. And the azimuth on the left is the degrees of rotation from true north. So north is true north, 90 degrees is east, 170 is almost south, and 180 is completely south. And I've coloured it so green is good, yellow is not so good, red is poor. But let's actually look at the numbers. So let's say we've got a south-facing array on a 20-degree pitched roof in Wanaka. So 23 degrees, pretty common roof pitch. So a south-facing roof in Wanaka, its annual average production or surface production available is 3.29 peak sun hours. But how does that compare as a percentage to if we'd face those panels north? So let me, where am I? Let me bring my little calculator up. Here we go. And get a calculator going. Right, so I'll take the I'll take the real for south facing at 20 degrees, 3.29, and I'll divide it by the north facing, which is 4.6. So it's telling me it's 71%. That south roof in Wanaka has got 71% of the potential of a north-facing roof in Wanaka. 71% is not nothing. A roof with nothing on it is nothing. So suddenly that south-facing roof, particularly in summer, is actually pretty damn useful. You'll be surprised how much it produces in summer because certainly in Wanaka, the very wide arc of the sun. The south-facing roof will be getting the sun before the north face even sees it in the morning. And it'll be getting it late in the afternoon when it's long left the north face. So in summertime, it'll actually have very good ends of day production. But just to contrast Wanaka with, say, Brisbane, and, well, of course, Brisbane latitude, I think about 31 degrees latitude, so a lot closer to the equator. So its south-facing roof is 4.6 peak sun hours. That's the same as Wanaka's north-facing, right? Oh, hang on. Sorry, I forgot to bring it up. There it is. Got too many screens running. So this is Brisbane's solar radiation data averages. And so a south-facing roof in Brisbane is as good as a north-facing roof in Wanaka on annual average production. And if you look at the variation from summer to winter, from north to south for Brisbane, let's plug those numbers in. So Brisbane, south-facing is 4.6 peak sun hours. Divide that by the highest number you can get facing 20 degrees north, 5.7 peak sun hours. So that south-facing roof is 80% as good as a north-facing roof in Brisbane. So pretty good result. And when you compare it to Wanaka, it's a huge result because it's actually just as good as a north-facing roof in Wanaka. So yeah, latitude is king when it comes to what the effect of different orientations and different tilt angles are. So there you go. Now I'm just looking at questions. Yariv has to go. Thanks. And do not permit this due to clash with electrical safety regs 2010. Your thoughts? Shall we agree on the DSP? Sorry, Yariv, I don't think I've followed your questions properly. Oh, here we go. So you start with 4777 Part 2. Part 1, 2024 is not cited. That's right. So we're expecting a couple of years. In the meantime, some networks have adopted it and permit greater than 30 kVA without secondary protection. Yes, I guess you're still in the old 4777. I think you're under a 2007 version, which is so out of date, it's not funny. So in practice, DNSPs, or lines companies as they call it in New Zealand, will require often a later version compliance because it's their lines and they can say what the rules are. So there you go. Okay, have I covered all that? Let me see. I've got the orientation, and yeah, I think that's it. Wow. So I'm just checking to see if I've missed any questions. No, don't think I have. Okay, wow. Yeah, I managed to nearly fill the hour. I wasn't expecting us to run the whole hour today because I didn't have a lot. So anyway, just to sort of finish up, thanks for watching, everyone. Really appreciate it. And I won't ask you to like and subscribe because you probably already have, right? Yeah. All right, it's time to go. So thanks once again. See you next week. And Ian, that's a pretty last minute question. I'll talk a bit about sodium-ion batteries. I'll add that to next week's Toolbox Tech Talk. All right, I'm out.
Every word that comes out is a lie. Make it look like it's so ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable. Fade out of the ground, you ain't no one. You will start, blow it up like supernova. In the nighttime, hit my hotline. Sharing secrets, you wish really was part your life. Basic bullets, with no bullets. Does your wife know you're begging for my notice? Promise you're the same, running for the